First of all, let me thank the organizers for the invitation to speak here and for organizing this very nice meeting. So the topic is has to do somehow with integrability and a little bit of machine learning on the very sides, but mainly it is a supergravity talk. It has to do with specifically with two-dimensional supergravities and gauged supergravities in particular. So I will start telling you a little bit what this is about with a little drawing. Let me start from the very beginning of the story. In supergravity, we often start with some sugra in 10 or 11 dimensions, for instance. And the simplest thing we can do is compactify a torus to generate a lower dimensional supergravity. Supersymmetry is preserved in the process. We cut all the massive Kaluza Klein modes, and what is left has a much larger global symmetry group or algebra. But that's a little bit boring. So just from the point of view of the low dimensional theory, one may take some symmetries and gauge them. And that gives rise to what we call gauge supergravity. So essentially that's general relativity plus a bunch of matter fields charged under some Yang-Mills group plus supersymmetry putting everything together. So if maybe machine learning people are not familiar with supergravity, that's what we're talking about. But of course, the interesting situation is this arrow here. We may start from 10 or 11 dimensions supergravity, which is interesting because it's low energy effective action for certain corners of string theory. And we want to compactify on something which is more complicated than just a torus, and perhaps truncating away the Kaluza Klein modes and keeping only some subset, we may again end up dealing with a gauge supergravity. So why? Why do we care about this? Well, as a simple example, let me give you some very well-known prototypes. The standard maximally supersymmetric ADS solutions. Each one of them associated to some brane and of course some dual theory. Each one of them associated to some truncation on the sphere, giving you a gauge supergravity with maximal supersymmetry living on the external spacetime and with a solution reproducing these ADS factors here. And then, of course, having many more other solutions. So this is just a very short example, but the list grows much bigger if you start looking at more complicated geometries, perhaps breaking some supersymmetry in the process of truncations. And of course, these are very rich theories with lots of solutions. And so you don't just find these solutions here, you start generating way more. Why do you use it? Well, for solution generation mainly. Maybe look for other ADS vacua if you're interested in holography. Black holes, domain walls, dual-to-RG flows, or even just exploring the landscape in a way of gauge supergravities and trying to figure out whether there are interesting models which you may then want to uplift. So you find a model here and you want to go back and figure out where it comes from because some of its solutions look very interesting. And in fact, you can do a little bit more. When you learn to do these things, you may have control over the Kaluza Klein spectra of the solutions you construct, for instance. And so you can answer questions about stability of non-supersymmetric solutions, for instance. So as a very quick example, when I look for ADS solutions, I usually take a scalar potential of a gauge supergravity. I'm not displaying what it is because it depends in the case of SO8 gauge supergravity on 70 scalars, so it's not a nice expression written fully. Not even sure anyone has ever written it fully in this sense. You find extrema, and these correspond to other ADS solutions with internal space some deformed sphere. So you will break the symmetries and supersymmetries at least partially, and that's a small plot with just a couple interesting points. This can be done analytically when you truncate to few variables, or it can be done numerically. And that's where some of the tools used in machine learning start showing up. This is a paper from a few years ago by Thomas Fischbacher and collaborators. Thomas Fischbacher will speak tomorrow. I'm not sure if he's going to mention this, but I will. This is a paper by him where he starts looking at this is a small set of the solutions they find for this very theory here, SO8 gauge supergravity. And they are related somehow by how the slope function works. But you can find many more, and there are many more models to explore. Okay. So that's just an introduction on why you might want to look at some gauge supergravities, but I haven't said anything about 2D. I want to do 2D essentially because it's not like we know everything in higher dimensions, but 2D is more complicated, and so far we didn't really have the tools to explore it. So I'm going to tell you what those tools are because we are finally being developed. But then maybe why do I care about 2D? Well, the obvious thing is maybe I want to look for ADS solutions, and ADS2 is the obvious piece of geometry you find in near horizon geometries for black holes. So it seems quite relevant to want to know how to construct such solutions. And the prototype, just like those in the previous slide, would be stack of the zero branes, giving you some metric which is conformally ADS2 process 8, not really ADS2 process 8. There's a running dilaton. This is not a conformal brane, and there is some flux, of course. This is a well-known solution, which leads also to 11 dimensions. A conjecture dual is a BFSS matrix model. And you can study other deformations like DMN, massive deformation, thermal deformations, and so on. What concerns me in this talk is the fact that it looks a little bit like those other prototype solutions, right? So is there a gauge supergravity associated to it? Well, yes, there is one, SO9 supergravity in 2D. You expect this to capture some of the lightest modes around S8. They may not be light when you go very far away from roundness, but still you capture those modes. But a proof of this has been lacking for a long time. Only a very small subsector was uplifted in these papers and used to study several types of solutions. But the full theory is quite another beast. And one of the points of the tools I'll develop throughout the paper is that, throughout the talk, is that one can actually construct and embed any field configuration of the steering, which I haven't defined for you yet, so you'll have to trust me for now. Any field configuration of this theory can be embedded into 11D supergravity or type 2A supergravity, as you prefer. And any solution here becomes a solution in higher dimensions. So that's one reason why I like to do 2 dimensions. But I can be a little bit more broad and look at more general questions. Maybe I just want to understand the structure of 2D gauge supergravities. This hasn't been entirely understood until recently. I'll be more precise later about what was and what wasn't. What does it mean? Well, 2D supergravity has an infinite dimensional symmetry group, a sibling of the Geroch group of general relativity with 2 isometries. Gauging means breaking these global symmetries. And then you may look for solutions, but you need to know the theory. You need to know the full dynamics, and that's not so easy to construct into it. And then maybe I might want to study compactifications leading to such kind of models, not just the 8 sphere, maybe something more exotic. And of course, vice versa. If you start in 2D, you want to uplift your solutions to 10 or 11 dimensions, you need uplift formula, a dictionary from the low dimensional theory to the high dimensional one. And in fact, this is going to sound a little bit out of place now. I want to organize the full dynamics of 10 and 11 dimensional supergravity in terms of the structures that appear here in 2D. Do I really need to? Well, it turns out that this is the key to solve the other problems. And it's interesting per se that I can actually do this. I can make a 10 or 11 dimensional supergravity theory look like a 2D supergravity and somehow see the Geroch group appearing, even if it is not a symmetry in 10 or 11 dimensions. And in fact, the logic of the talk is somehow that I need to do the opposite of what I just told you. I start from the bottom, solve what looks like the most complicated problem, and that's what allows me to finally learn about 2D gauge supergravities. Okay. Any questions up to here or complaints? Okay, very good. So let me first focus on the symmetries of the problem. I have to tell you what these infinite global symmetries are. So let's go from higher dimensions to 2D. Now, let's do it in steps. Let's suppose I reduce from general relativity down to 3 dimensions. I don't promise that all the coefficients and signs are right. I hope they are, but don't use this in production environments. When you reduce your 4D theory, your 4D metric in 3D, you gain a vector field, a Kaluza Klein vector field. But in 3D, vector fields are dual to scalars. And when you do this dualization, you gain an SL2 global symmetry, which is manifest in terms of the axiodilaton. The axion is psi, the dilaton was already in the metric, the size of the internal circle. Okay, that's very easy, but now let's go to 2D. I'll drop the vector fields now because they are non-dynamical in 2D anyway, for now. I'll have to recover them later on. I went to conformal gauge just because I like it. That's not strictly necessary. There is a residue of the vector field in 3D, which is this little a, which is still dual to an axion psi in 2D now. And this way I recover the same global symmetries I had here. That makes sense. I could reduce from 3D to 2D, so the symmetries have to be there. On the other end, just look at the metric. That's a 2x2 matrix. And I have a structural group of my internal 2 torus, which is again SL2 plus a volume. What happens when I start combining these two symmetries? Well, they don't close. They generate a full infinite dimensional group, which is a loop group over SL2. For experts, this is the Ehlers group, this is Matzner-Missner SL2 group. Together, they generate the Geroch group, essentially. And this R plus is the derivation. And here R plus was just the volume, the rho factor, essentially. Okay, maybe I went too fast. You can interrupt me if I go too fast and I switch to the next slide too quickly. Now, this was the logic just for GR. You repeat it for maximal supergravity. Just some names change. The Ehlers group is enhanced to E8, while the structure group is enhanced to a larger one because you have more internal dimensions. When you put them together, you get something called E9. But morally, we are still doing the same thing you will do if you're familiar with the Brighton-Lohner-Mason linear system. Okay, you just have slightly larger matrices showing up. Okay, so let me get to the Brighton-Lohner-Mason linear system. I'm going to assume I went through the trouble of reducing to 3D and then 2D, and I'm going to take a Lagrangian for two-dimensional gravity, which is the dilaton times Ricci scalar written in conformal gauge. Rho is the dilaton, sigma is the conformal factor of the 2D metric. These are currents for some nonlinear sigma model, which may be SL2 for GR or E8 over spin 16 for maximal sugra. So this is manifestly invariant under these global symmetries here. And little v is just the coset representative for either of these. The equations of motion are easy. Box rho is equal to 0, and then there's a conservation equation for the currents. You'll see why there's a P0 later on. But now out of these equations of motion, I can generate dual potentials. At least one for the dilaton, that's quite obvious, but an infinite series of dual potentials for my nonlinear sigma model. If anyone in the audience is familiar with the principal chiral model, that's a similar story, just there is no rho there. And that makes it much easier actually in the next steps. Here it's a bit more complicated. So how can I capture all of these? I don't want to generate infinitely many duality equations. That's quite inconvenient. Well, there are many ways to do it. I'm going to follow Brighton-Loner-Mason. I introduce a generating function. For the experts, I'm using different conventions. So stuff which is regular at 0 for me is regular at infinity. Don't be annoyed by this, please. I define an object depending on a spectral parameter. That's an auxiliary constant. These objects I expect to be my original closest representative plus a bunch of extra terms. It still needs to be valued in E8 or SL2, whatever it was. And it has to be it needs to satisfy some regularity conditions at W going to infinity. And somehow I identify this object as being generated by my dual potentials. Okay. Once I have it, I impose a linear system, which is tailored so that the Cartan-Maror equation for this object here, translated to the left-hand side, reproduces the equations of motion and nothing else. So these coefficients here, Q is just the anti-Hermitian part of the derivative of the physical scalars. It's the composite connection. These weird coefficients with this weird function gamma here are there because that's what I need in order to reproduce these equations of motion with this rho factor in particular, which is the cause of all the trouble, okay, which causes this very weird function. And I believe at this point, you could say from here, one can move to something called a monodromy matrix associated to the branch cuts here and discuss solution generation in terms of the monodromy matrix. I'm not going to go that way. I think there will be a talk about these things though in a couple of days by Cristina Camara. Instead, I have a few problems with this. For what I need to do, this is slightly inconvenient. It does capture all the dynamics I need, but I want to break integrability and I cannot really use this in this form. So what are my troubles here? First, I used an E8 invariant formulation, or covariant at least. But if I were to reduce from 11D to 2D directly, I wouldn't see E8. I would only see some other GL9, which is not even a subgroup of E8. And it's unclear how to write this in that case, okay? So there's a different duality frame in a way. And I don't know how to write this system in a different duality frame. This is gauge fixed to a specific parabolic gauge for this generating function. It has to do with the regularity conditions I imposed here. And moreover, I have a bit of problem with this square root because at some point I will need to write these objects in a highest weight representation. So that they're going to be operators acting on something, on some Fock space in a rough way, on highest weight module really. And there is no W there. Okay? There is no notion of a function of a spectral parameter when I work in highest weight representations. I just have a bunch of operators. So there is no expansion in terms of W here, and these are exponentials of generators of some Kac-Moody algebra. There is no W showing up. Okay, there is a loop mode, but it's just an integer number, a grading for my algebra, and nothing else. There is no actual parameter I can put in a square root. Okay, so how do I handle this? This is where we leave Brighton, Loner, and Mason for the experts. I'm going to notice that this function gamma, I'm going to explain this a little bit, but not entirely. And I'm going to do it for a dilettante sector where it's a little bit more manageable. And then I'll just tell you the result. So the gamma function I showed here solves this equation. You see star d rho gives you a d rho tilde, which is the dual scalar. But you can see there's some kind of geometric series showing up here. So let me expand it. And then let me decide that this function here that I'm looking for is not a function. I'm going to make it a little bit more general. I just need it to be some formal power series. I don't care about convergence for now, but I will be happy if at the end of the day I find a convergent series. Why do I want it to be a formal power series? Because then I can reinterpret a series like this, if it is formal, as an infinite product of exponentials of derivatives of the spectral parameter. And these derivatives I gave a convenient name, L, which hopefully already reminds you of Virasoro algebra. Okay? So now I have to solve this equation, expanded, along gamma going to infinity. But I want to rewrite it in terms of this operator here. When I do that, I lose track of any square root. There is no spectral parameter in sight anymore. As long as the commutation relations of these objects are meaningful, and they're going to be those of the Virasoro algebra after all, then this is the equation I need to solve. Okay? So now I have an operator, gamma, that can act on a highest weight representation and somehow encode the same knowledge at this little function here I had before. Okay? Sorry for going back and forth. And in fact, if I take the Hermitian part of this d gamma gamma inverse and call it P, there's a very short version of this equation, which is shown here. Star P is equal to, well, W times P. Okay, I put a spectral parameter there. I forgot about that. But in fact, W times P, I can call a shift operator. It just means that any generator that shows up in P, it may be a loop generator, maybe a Virasoro generator in this case, is shifted by some number, 1 in this case. Okay, so it's just telling me that each component of P is related to each other up to an Notch dual. And that gives me this equation. And I'm going to do this for the rest of the generating function as well. Once I do it, I define a larger coset representative containing this group element, which is some kind of Virasoro group in some sense, and then the abstract version of the generating function, which I'm now calling D loop. And if I take the Hermitian part of the Cartan-Maurer form of V, so dVV inverse plus Hermitian conjugate, I call it P usually throughout the slides, I have that my linear system reduces to this expression here. Star P is equal to P shifted, mode number shifted. And then just because I have a central charge here associated with the conformal factor of the 2D metric, the shift operator has no meaningful action on the central charge. The best thing you can do is just set it to 0. And then you have to compensate for it with an auxiliary form. I don't strictly need to put this here, but I will need it later. Okay, in a sense, all this is telling you is that the central charge component of this equation is pointless. It doesn't contain any information. Okay, what I care about are the other components. Okay, questions here? Yes, yes. I somehow skipped showing all the commutation relations, but yeah, maybe it's the next slide, I think so. But yeah, K is the central element of the Kac-Moody and Virasoro algebra. They are, of course, there is only one central element. But most importantly, I don't need this expression for my generating function. I'm not going to call it generative function anymore. It's just V loop, an element in the loop group over E8. It can be in any gauge. And that's important to me because I might prefer a different gauge after all, for instance, when I reduce from 11 dimensions. And that wasn't possible from Breton-Lohner-Mason. So this is the setup I have. It's quite different from what is being used when one talks about the Geroch group and Riemann-Hilbert factorization, for instance. But that's the one that I can use to study compactifications of supergravity theories. Okay, just a summary. This curly V I showed you has some gamma, which is this Virasoro group defined in terms of formal power series, and then a loop, an element of the loop group over E8. Eventually defines a coset space, which is this infinite dimensional coset space here. That's twisted set duality as I just defined it. And just to tell you what the meaning of this is, you have the original isometries, which are the 0 modes of the loop algebra. The central charge, that is the central element, is associated with the conformal factor of the external metric, rescalings of the dilaton, shifts of the dual dilaton, shifts of the dual potentials, and a bunch of hidden symmetries. Okay, and that's it. That's the whole theory. Okay, The dynamics are completely fixed by this, well, up perhaps to the Virasoro constraint for the conformal gauge, but that's kind of obvious. And the equation of motion for sigma is anyway solved from the Virasoro constraint. So you have everything here, everything relevant is here. Despite that, later on I will need actions. So I need to have an action that I can handle so that I can then deform it by adding a scalar potential, gauge couplings, and so on. So I'm going to write an action even if it is completely redundant because I already have all my dynamics there. And since actions are never going to be invariant under all these symmetries, I'm going to write a pseudo action first, one which you need to vary and then impose twistor self-duality on top of it. So definitely redundant here because twistor self-duality is already all the dynamics. But I'll do it anyway. And I'll start from the Bianchi identity for my currents. Q is the composite connection, which you get again from curly B, from my scalars. That's just an identity, but let's suppose for a moment that I shift it anyway. I apply a shift operator and I forget that this is 0. I just treat these as formal objects transforming as they should. Then I might say, well, the inside here is an algebra element. It transforms as an algebra element. But the shift operator breaks that, especially because of the lack of a central charge element. So let me add it back. And I already decided to call this my Lagrangian for some reason. Let me explain you why. I add it back so that the whole expression is again covariant. So it transforms as an algebra element. It transforms with a commutator. Okay, under a symmetry of my theory, this thing transforms into the commutator of itself with the symmetry generator. But now let me remember that most of this was already 0. So this is an algebra element, which is in fact only proportional to the central charge. It transforms with a commutator, but the commutator is 0 because it's a commutator with a central charge. So this expression here, which is really only this expression here, is an invariant. So I have constructed by this slightly simplistic trick, maybe, I can construct explicitly a pseudo action for my theory, which is, at the very least, it is invariant. I still have to check whether it's the correct action to have. And I'll cut it short and say, you do compute the equations of motion and check that it is. There is a little ambiguity here. You could add an invariant with something which is invariant by itself, and it's not entirely fixed by the construction here. But the only part which is not obviously fixed, you fix by checking the equations of motion. And I'm not going to show that because it's a bit too long. And it has a nice interpretation. It's just the Q covariant derivative of the auxiliary one form that showed up in twistor self-duality, up to a weight factor of rho. Technical detail. Questions up to here. This was all just 2D supergravity, or even just 2D gravity, GR restricted to 2 dimensions, with 2 isometries, just written in a different way. And now I have a twistor self-duality, and I have a pseudo action, which is redundant because twistor self-duality already gives me the whole dynamics. Now the next step is I want to break all of this, okay? I don't want to be integrable, I want to break integrability. But, oh yeah, I forgot a piece, sorry. I kept insisting that there are different duality frames and I needed a duality covariant formalism. Let me finally show why. Remember, I could go from 11D to 3D. When I do this, I generate a bunch of vector fields, but I can dualize them into scalars, just like a few slides ago when I was showing you the big matrix of the metric. I get an E8 symmetry, and then I reduce to 2D. I get this very nice Lagrangian we saw earlier as our starting point. But why do I have to do that? Let me just reduce directly. I get what I get. I don't care. I get, perhaps it looks a little bit uglier, but I have the internal metric up to the conformal factor of rho. Now it's the internal one. And I have an internal freeform with upper indices just because of my mistake in choosing the wrong conventions when I wrote this. And this is, somehow you can see this is the Jean-Simons term in 11D supergravity reduced to 2D. Okay, so you can see it's very different structure than here. Here there is an obvious SL9 manifest symmetry, but this SL9 is not even contained in E8. It's a different one. It is with different degrees of freedom. Okay, it's like the Massner-Misner versus the Ehlers groups in my earlier example. So why am I showing you this? Because you could ask, how do I go from this to this if this is the same theory? To do it in 2D, I might want to do something people do, for instance, in non-abelian duality. I gauge the isometries associated with the degrees of freedom that were dualized here. I impose a Lagrange multiplier to put the gauge connection to flat, and then I integrate out the gauge connection, and I should end up here. That's laborious. And it's going to be even more laborious if I want to do it when I have a gauge supergravity. So I don't want to do that. But my pseudo-action comes to the rescue. The idea is that I can take my pseudo-action, that topological term, that decay that I showed you a couple slides ago. And in fact, if you just carefully reorganize the terms in that action, you'll see that it shows up as a physical Lagrangian. Which one of the two in the previous slide, I'll tell you in a moment, plus a bunch of squares of the twistor self-duality constraint. Now, this is a pseudo-action. So when you vary it, you have to impose the twistor self-duality equal to 0. So the variation of this part certainly doesn't contribute to the equations of motion, and you're left with your physical Lagrangian. So you can recover the physical Lagrangian with this trick. Just to give you an idea of how it looks, in the sector which only sees the dilaton and the conformal factor of the center of the external metric, the action looks like, the pseudo action looks like this, and after some manipulations you get the dilaton Ricci scalar term in conformal gauge. Conformal gauge is not necessary, but it's faster for the slides. And then these are just twistor self-duality square. Twistor self-duality for the Virasoro currents, twistor self-duality for the auxiliary one forms. Okay. Okay, very good. I'm not going to show you how to do it for the rest. That will take a couple slides, but it's the same idea. Okay, it's just completing the squares. That's it. Algebra, nothing more. Depending on how I choose my parabolic gauge for my scalar fields, this trick gives me either physical action or any other one I might like to generate. Okay. So somehow this is a nice bookkeeping device, which is agnostic about my choice of duality frame. And that's quite convenient. And it is also manifestly invariant under my global symmetries. Okay. Questions of any kind? Well, that was not expected. I think the talk is over, but that wasn't my intention. Is there a mouse here? Okay, sorry, I'll figure out what is going on. I did check my slides before loading them here. USB. Maybe the USB. Let me open this again. Let me close this entirely. I don't know why I say it out loud. Let me just check that the slides are actually there later on. This stuff wasn't shown yet, so I think so. Is there? It is there. Yeah, I don't know what happened. Where was I? Okay, crisis averted. We were here. Okay. Fingers crossed? Yes. Okay. Sorry about that. Any questions in the meantime? No. Okay. So next step, I told you about the global symmetries, and somehow I rewrote a very simple theory in a somehow more complicated way, but which I find more convenient. At least it is covariant under my infinite global symmetries, infinite dimensional global symmetries. Now I want to gauge some. And I'm not going to worry about the higher dimensional origin yet. But in order to gauge, well, what does it mean to gauge? I take some of my algebra generators of G. I take my vector fields, which so far I had just forgot about, and I couple them, and I put them in a covariant derivative. And the matrix that does the job is usually called an embedding tensor. But I'll just call it theta, okay? That's just the matrix that shows up here, whatever it is. That's the basic idea. But how do you do it in practice? Well, in higher dimensions, everything is very well understood, thanks to supersymmetry. And there are a couple lecture notes here, just if you're interested. But to make it sound very, very simple, you covariantize your derivatives in order to gauge some subalgebra of your global symmetries. And then you realize that your SUSY transformations are not preserved anymore. So you correct the Lagrangian by mass terms for the fermions, and you correct the SUSY variations of the fermions, all by term proportional to the gauge couplings, theta. And then things don't work yet, but they almost do. You just have to add a scalar potential, a potential for your scalar fields at second order in the gauge couplings to restore supersymmetry. So this is a very well-known procedure. Okay, I'm making it sound easy. It's not necessary depending on the theory, but it can and it is being done. Unfortunately, in 2 dimensions, it's very hard to do this. The reason is that this object here transforms covariantly under my global symmetries, which are infinite dimensional now. It's E9, it's an infinite dimensional group. Fermions should transform under the maximal compact subgroup or maximal unitary subgroup of E9, K of E9. But the representation theory of this is not really well under control, so we cannot follow this procedure. Basically, we do not have enough control over the couplings of the fermions to do this. So, for the sake of looking for solutions, maybe with machine learning, maybe just because I like to find some new black holes, I need the scalar potential and I don't know how to find it. Okay. In fact, up to the scalar potential, there is a full construction of gauge supergravities into D by Samtleben and Weidner, which relied on the Bright-Lohner-Mason linear system and not on this Christoset duality I displayed to you. I will not review it, otherwise it will take too long. But the big missing piece was the scalar potential. But then, let me remind you what the idea was. The idea is that I have to solve something much more complicated, reorganize the full 10 or 11 dimensional dynamics in terms of the structures I showed to you until now, compactify down to 2 dimensions, and then finally I can learn about the structure of 2D subgraphs. So this is going to be my strategy. I cannot use supersymmetry in 2D. Instead, I'll have to go from 11D down to 2D in order to figure out the structure of these theories. So this means that I have to introduce something which is per se a very big topic, and I will just squeeze it into a few slides. So inevitably, you won't get all the details here. The idea is to use something called exceptional field theory, 49 in our case, but let me first introduce the general ideas. The idea is you start with, for instance, 11D supergravity. You have a metric, a 3-form, a 6-form, dual to the 3-form, and blah, blah, blah. Mixed symmetry potentials dual to this stuff. And you have, you do the same stuff you will do under a Kaluza Klein reduction. You reorganize this stuff in terms of the degrees of freedom you would have in a lower dimensional maximal supergravity. A metric, scalars parametrizing ED over the compact subgroup, vector fields, 2 forms, blah, blah, blah. But you don't drop coordinate dependence, okay? These are fields depending on 11 coordinates still. But then what happens to all the gauge symmetries along Y, along the so-called internal space, since the dependence is still there? Well, I have a change of coordinates and gauge parameters for these P-forms. They end up being reorganized into something called generalized diffeomorphisms. Basically, they end up in a big vector. This big vector is the parameter for a big version of a Lie derivative called a generalized Lie derivative, which can act in a well-defined way on these objects here, which I remind you are just a repackaging of your 11D supergravity stuff. So how does this look like? I have a transport term, and then the rotation term is projected to not rotate just in GLD, but to rotate with an element of ED, which is fine because each one of these objects sits in a representation of the exceptional group, ED, E9 eventually, okay? I have to construct the right projector with the correct coefficients in front and blah, blah, blah. I'm going to skip all of that. This is a well-known structure that one can construct. Then you might complain, though, that I didn't tell you what this dm is. I haven't even told you what this capital M is. Capital M is some representation of the exceptional group. For E9, this is going to be an infinite dimensional representation, but I definitely don't have infinitely many derivatives along the internal space. The idea is that there is a way to embed the physical derivatives in this formal operator. And the trick is, as long as I don't look inside it, all the expressions are right, look covariant under my exceptional group. So I can pretend that I have covariance under my E9 group, but it's only a formal one because at some point I need to remember that I don't have infinitely many directions. And in fact, there are two ways to solve this condition here, that I only have finitely many internal directions, and that allows you to treat 11D or type 2B sugra at the same time. So that's quite powerful because you have one formalism for all maximal supergravities. That's admittedly very short, but the idea is that you don't need all the details of this. You just need to know that it can be done for E9 as well. You don't need to care about the details, just know that there is this M index corresponds to a certain representation called the basic one. Basically, the first representation you will define. It is a highest weight representation, hence this kind of definition in terms of a vacuum state. You can branch it with respect to E8 if you like, but it doesn't really matter. There is a nice definition of generalized diffeomorphisms for E9. And now you might wonder, but do I really need to take 11D supergravity and rephrase it in this framework? It looks like it's extremely painful. The answer is no, of course not. The whole point of this is once you know your gauge symmetries, you construct your theory not by comparing with the 11-dimensional supergravity. You just construct it by imposing your symmetries. And eventually it will turn out that your theory reproduces the same dynamics as 11D sugra or type 2B. I'm not going to go through the details of that. I will just tell you what's the idea. The idea is I want to take maximal supergravity in 2 dimensions and impose that my fields depend on internal coordinates and have these gauge symmetries. So I covariantize with respect to generalized diffeomorphisms. And then I will need to add a scalar potential. But this time I know how to construct it. I construct it by imposing gauge invariance. So first step, imagine I take my original 2D supergravity we described at the beginning with the V loop and the curly V. I make them depend on some Y coordinates, which may be infinitely many, and then I will later remember that there are only finitely many. I take my generalized Lie derivative with parameters, some vector fields, and I use it to covariantize my 2D derivatives. Now, you might remember how I constructed a topological term for 2D gravity. I took the Bianchi identity for my currents, shifted it, and completed it with an extra central charge. And that completion was the action. I do the same, but now the Bianchi identity involves field strengths for the vector fields. I refuse to show them. It will just be annoying to see it. I just follow exactly the same procedure, and I will get the new action. Okay? Just by shifting the Bianchi identity of my scalar currents. And it will look like like before with covariant derivatives and a bunch of field strength terms that are a little bit ugly and I'm happy to hide. But there are finitely many anyway. And then I need to add an extra term for consistency of my theory. This term, I cannot use these tricks. It has to be computed from scratch just by imposing gauge invariance. This has been done a few years ago by these people here with me. And you don't need to understand the formula, just know that there is some extra expression that has to be dealt with. But the important point is this will be the scalar potential in gauge supergravity. Now, in gauge supergravity, I don't know how to construct it, but here it just descends from the symmetry structure of exceptional field theory, and it is a fixed quantity. So now my claim is put this one and this one together. You don't need to read the details. Put these together with physics duality gauged with this covariant derivative. You get the dynamics of 11D supergravity or type 2B. It doesn't look like it if you just look at the slide, but this is the case. Okay. Questions? Can you? The question is, in what sense this is the curvature, this one? Well, it's a curvature with respect to a connection along the internal space. Yeah, so one way to put it would be you can covariantize these internal derivatives. You introduce a connection. It is generalized because it has to respect the structure along these big indices. It has to sit in representations of benign. Yeah. And eventually, you could try to follow that route and eventually show that that connection gives you a curvature, which is this. In fact, it turns out to be easier to not do that. And you just construct this from scratch, just by hand. It's easier than trying to construct the curvatures in this case, because the curvatures will require handling K of E9, and that's hard to do. But that is in the sense in which I say an internal curvature. It's for a generalized connection along the internal generalized one. Okay. Okay, so somehow we very briefly solved the first problem. Now we can go up and try to get to the main question. But to do that, we need to do compactifications with this formalism. Meaning we need to worry, that looks a little bit ugly, but we need to worry about the diagonal slice of this graph. So let's take a step back and make things a little bit easier. I want to get a gauge supergravity by compactifying 11D or 10D subgraph. Who cares about exceptional field theory for this in the next slide? How do I get a gauge supergravity? Well, it's really a consistent truncation of some theory on some background. What I mean is I take 11D supergravity on some background and show that if I only pick some fluctuations around the background, the equations of motion of those fluctuations organize into a gauge supergravity in lower dimensions. And all the equations of motion of my theory are those of the lower dimensional theory times some geometric data. If this stuff is zero, then the left-hand side is also zero. So all solutions in 2D are solutions in 11D. Okay, so that's the idea. This is not necessarily an effective theory because I might be capturing heavy fluctuation modes and dropping modes. What matters is consistency at the classical two-derivative level. And the simplest example is Church-Schwarz compactifications. This can be done just in GR, so no exceptional field theory yet. You take a metric, you decompose it a la Kaluza Klein. I'm still keeping all coordinate dependence as usual. Let me focus just on the internal metric and Kaluza Klein vector fields. If my internal space is a group, is a Lie group, it has invariant, left invariant forms, and I expand all my fields in terms of the left invariant forms. The coefficients I claim only depend on the 2D coordinates and not the internal ones. If that's the case, I end up with a gauge supergravity where the gauge group is nothing but the gauge algebra on my internal space. And why is that? Well, essentially because the duals of these forms are vector fields that are the killing vectors on G and satisfied at the algebra. So now I do need to go back to exceptional field theory. I want to do exactly the same trick, but not in terms of this G and this K, in terms of the XFT fields. So remember, I was taking my theory, rewriting it in terms of exceptional field theory objects. These are really the objects that look like 2D supergravity objects, but depend on internal coordinates. And then I factorize the dependence on the internal space in terms of a generalized frame, the equivalent of the little e in the previous slide. There are some factors of determinant you can completely forget for the sake of the talk. And eventually, instead of having the Lie derivative of two vectors giving you structure constants of a Lie algebra, you have a generalized Lie derivative between two generalized frames, giving you the embedding tensor that appears in gauge supergravity, appears in the covariantization of derivatives in gauge supergravity. And this is the condition you need to solve, okay? This is a differential condition. It can be very hard to solve, but that's what you need to do. Now, I'm not going to find all solutions to this for you because nobody knows how to do that, even in higher dimensions. But I'm going to assume that one can do this, okay? And there are examples where you can do it. If I assume I have solved this and for a certain theta, what can I do? Well, that's technical stuff. Don't worry about the details. Just know that eventually the embedding tensor, this theta that shows up in the covariant derivatives, becomes just a bra. And it has an expression in terms of derivatives of the frame. That's all you need to capture from this slide. Forget about the rest. So if I have an E, I know how the embedding tensor is related to the frame. It's some expression here, whatever it is. Now, I'm going to plug this knowledge in my dynamics. So remember, I don't know how to find the scalar potential of gauge supergravity because I don't have SUSY in place in 2D. But instead, the generalized diffeomorphisms were enough to fix the scalar potential of exceptional field theory. This is just part of the dynamics in 11D supergravity, written in a very complicated way. But this one I can reduce following the factorization ansatz. And of course, I'm not showing the computation here. After a little while, you find an expression in terms of the embedding tensor for the potential of 2D gauge supergravities. And this is new. Okay, this is a first. Okay. This is not fully general because it only applies to those gauge models which do have an higher dimensional origin, which can descend from 11D or type 2B supergravity. So it's not 100% general, but these are the models we care about anyway. Any questions? Okay, so this was the most important message. But now we can try to use this a little bit. I don't plan to say much about it, but I will say a few things. So first of all, let me remind you what was the #1 motivation to do all of this. I will not go through the details. I will just repeat the claim. I think there was enough technical stuff for one talk or two probably. One idea is to reproduce SO9 gauge supergravity, which is what you should get when you compactify type 2A supergravity on an 8 sphere or 11D on S8 times S1. That's a typo. That's an S1. And the reason we care about it is related to physics of a stack of D0 branes and to the BFSS matrix model and its deformations. And indeed, the claim is, go back a couple slides, allow me please. For the embedding tensor of SO9 gauge supergravity, I can find a frame that gives me this factorization ansatz for all my fields. Okay, I'm not going to show it, one, because it's actually similar to other spheres. The difficult part is everything else you need to construct before you can just plug in the frame that is somehow obvious to construct. It will take too long to explain why it is obvious, so I will just not do it, okay? But once you do it, any solution in this theory now can be lifted to 11 dimensions. And that was not allowed, was not possible until a few months ago. Okay, so that's one thing. And just for concreteness, this is the SO9 gauge supergravity. That's kinetic terms and topological. That's your scalar potential. Okay. So now one can say, this was already known, actually. This was the only one 2D supergravity which was constructed regardless of all these issues I discussed. Everybody's very welcome to start looking for solutions here for vacuum and so on. That's quite wild. So, and people haven't looked into it too much because we didn't know how to uplift the solutions, but now we can. So it would be nice to have analytic and numerical tools as well to analyze this potential. This theta here is essentially delta Ij, okay, that defines the SO9 group. Okay. But then I don't have only the potential. In fact, all the theory is defined in terms of a topological term that comes from the Bianchi identity with the usual trick and the scalar potential. But I said only the embedding tensors allowed are those with higher dimensional origin. You may ask, this theta here is infinite dimensional, no? That's highest weight representation of E9, that's infinite dimensional. How many gauges are there? Well, requiring that they do arise from higher dimensions restricts you to a finite number of entries. This is only necessary, it's not sufficient. You don't throw random numbers in here and get a sensible gauging. But yeah, that's what they are. So another thing one might really want to look at is to start constructing other models, not just SO9. Okay. But there are a bunch of constraints for this to work. I plug this into the quadratic constraint. This is just implied by the consistency of a gauge model, just invariance under gauge transformations of the embedding tensor itself. More constraints that show up just because there has to be an higher dimensional origin. And then, for instance, I might just look directly for radius 2 solutions. I take all the gauges I can have, and I look for radius 2 solutions in all of them at the same time. This can be done because my scalar fields parameterize a homogeneous space, so any point is equivalent to the origin. So in fact, I can always set my scalar fields to 0 when I look for vacuum, because they will be constant anyway. I stick to the origin. The transformation that maps me from a random point to the origin is an E9 transformation. I can absorb it again into theta. And so it's easy enough to look for, this is the extremum condition for the scalar potential. There's a T delta here that somehow corresponds to the derivative of a scalar. It's enough to set the scalar fields to 0 and then solve these algebraic equations to look for solutions. I say ADS, but there is no guarantee here that the cosmological constant is going to be negative. I'm just hinting at the fact that right now I'm more interested in ADS. But that's a bunch of variables. These are quadratic equations, but there are many quadratic equations in many variables. So this is a hard problem, and that's where analytics can only bring you so far, and then you need some numerics. Okay, that was it. This is just a summary. I'm not sure if I'm late. No, almost correct. So a reminder of what I've been doing, I've been talking about. I wanted to understand 2D gauge supergravities. Okay, they are related to classical integrability, which is maybe familiar from the Geroch group in general relativity. But what I really want to do is gauge the associated infinite dimensional group by breaking it and study the dynamics. I had to formulate those. I didn't know the scalar potential of these gauge supergravities until now. And now I would like to look for solutions. I care about these models because they come from compactifications of 10D or 11D supergravity. And we discussed a little bit what's the framework to understand all these relations, okay? So in the future, what should one do? Certainly study the D0 brane through this SO9 engaged supergravity. Look for new solutions and new geometries. In fact, one can use all this structure of exceptional field theory to do spectroscopy of a solution, not just engage supergravity, but in the full 10 or 11 dimensions in a very, very convenient way. It really simplifies the work of studying spectra or mass spectra or even higher order couplings. That's a paper from a couple of days ago, actually. And it would be nice to apply all this structure. I didn't know this would ring. It would be nice to apply all the technology of exceptional field theory and Kaluza Klein spectra, especially to this case, but maybe also to other geometries. Okay, but there is work to do there, just technical work to apply, to just construct the tools you need. And well, one last question is, of course, we are doing 2D. ADS2 related to black holes and extremal black holes. What happens when I start going away from extremality? Can I do JT supergravity for this maximal supersymmetric case? How do they relate to the D0 brane matrix model? These are things that I think are very interesting, and somehow I wanted to say more in the talk and then realized I'm still just too confused to say something. So I'm going to drop it there, and hopefully somebody will explain them to me after the break. So thanks a lot.
So I have a question about, you said you'll be using integrability in the gauge fix, right?
Yes. Do you need
in what sense? Why do you need to do that?
Well, you lose integrability in the sense that you definitely break the infinite global symmetries you have to, well, a gauge group which is infinite dimensional, but usually it's not enough to guarantee integrability. Like,
okay. So you're saying that in the presence of particles, so in the case of gravity, you would not see infinite number of conserved terms.
I would not say what?
Infinite number of conserved terms.
Not for global symmetries. The gauge group is infinite dimensional, but usually that's all the symmetries you have. You break the rest of your Geroch group. And usually there is there always is a duality frame in which your infinite dimensional gauge group is whatever acts on physical fields, and then just shift symmetries for dual potentials. So integrability in this, at least in this case, somehow has to do with the presence of hidden global symmetries, which relate dual potentials to the physical ones. And this is usually broken. Of course, if you pick a specific gauging, it might be that that specific gauging preserves integrability in some sector of your theory.
Okay, but okay, it's theories where you can go down 2 dimensions on the integral system, and where you have some nice full set representation, blah, blah, blah. Are you saying it might not be generally that's possible? Then generally you might not be good at a relaxed set.
Well, you can write a gauged version of the linear system where all the derivatives are covariantized, but that's not the same as having integrability.
Okay. Thank you.
A quick question. How much effort would it be to tweak the formalism to work in as a signature, like you wanted to do Euclidean?
How much of this changes for Euclidean? Okay, so the ungauged story at the beginning, so Brighton honor Mason and moving to a Christoself duality, I haven't tried, but I believe it should be the same. There are a few differences. Yeah, that was it. Okay. I cannot hear you. Sorry.
No, Brighton honor Mason works in either signature.
No, Brighton honor Mason, yes. Switching from that to twisted self duality, yeah, I believe should also work. I don't remember if it is in the Julian Nicolai paper or not, because we started using that and then we adapted. Gauging just into this should work similarly. The one thing that is not guaranteed to work as well is exceptional field theory. If you do exceptional field theory, where the internal space has the time contains the time direction, you could formulate that, but the consistent truncation is a bit tricky. The reason is this. Maybe this is it's a bit of a technical point, but it's also easy to show. The problem is this factorization here. Now, the problem is that this thing corresponds to the scalar fields. Now, the coset space for the scalar fields is not a symmetric space anymore. The denominator is not the compact subgroup, it's some other group.
Yes.
Non-compact. Really, the scalar manifold is only the Poincare patch of that coset space. But these matrices here usually do not sit in a parabolic gauge. Poincare patch means that somehow your coset representative sit in a certain parabolic gauge, even if the denominator of the coset space is non-compact. But these matrices here usually do not respect that gauge. And so these ansatz here may be just nonsensical.
Okay, thank you.
And this is a problem that I don't know how to solve right now.
Thank you.
Okay, let us thank you.
Thanks to you.